Welcome to the Sleepy Scientist. Settle in, let your shoulders ease, and allow the rhythm of your breathing to slow as the day gently drifts away. Tonight we explore the age of giant insects, a time when the air itself shaped creatures into astonishing forms. Vast forests of strange trees stretched across the land, and above them wings broader than a crow's shadow glided through heavy skies. It is a world both alien and familiar, and one that tells us something profound about the chemistry of life on Earth. Before we wander too far into that world, a gentle question. Where are you watching from tonight? Perhaps curled up in a quiet bedroom, or listening with headphones on a train winding home, or maybe somewhere completely unexpected. If you find these calm journeys help you unwind, it would mean a great deal if you could like this video and subscribe to The Sleepy Scientist. To those who are already subscribed, thank you for keeping these explorations alive and breathing. And a small, playful warning. The story ahead might be just engaging enough to delay your sleep by a little. But if it does, the silver lining is that you will drift off with new knowledge tucked gently into memory. So let us step softly back into deep time. When the air was rich, the trees were strange, and the insects were giants. What secrets does this ancient atmosphere hold? The world of giant insects did not emerge out of nowhere. To understand their rise, it helps to picture the stage they inherited. Over 300 million years ago, Earth was a patchwork of swampy lowlands and lush forests unlike anything you would see today. The trees were not oaks or maples, but towering lycopsids, plants that looked like oversized spikes covered in scale patterns, some of them stretching more than 30 meters high. Ferns unfurled fronds wider than doorways, and horsetail relatives stood in ranks along riverbanks like green scaffolding. The ground was soft with peat, the air heavy with moisture, and the canopy wove a ceiling that filtered sunlight into green dusk. Within this world, the very chemistry of the air tilted in unusual ways. Oxygen, the gas that fuels fire and breath alike, rose far higher than it is today. Instead of the roughly 1/5 we live with now, the air in parts of the Carboniferous carried nearly 1/3 oxygen. The atmosphere was richer, flames leapt more easily, and every spark found kindling in the dry season. This chemistry did more than feed fires. It whispered possibilities to the bodies of animals. For creatures that relied on oxygen spreading gently through their tissues, it meant a chance to grow larger, to push the limits of design. Insects, already among the most adaptable forms of life, answered that invitation in spectacular fashion. Wingspans stretched to nearly 70 centimeters in the griffin flies, ancestors and cousins of dragonflies. On the forest floor, millipede relatives longer than a human stride threaded their way between roots. This was not a world of monsters, but of scaled-up familiarities. Ordinary designs expanded to extraordinary sizes because the air allowed it. Yet the story is not just about size, it is about balance, between plants and atmosphere, between fire and flood, between the demands of body design and the gifts of chemistry. The age of giant insects becomes a lens through which to view how life and Earth co-create one another. Each tree that fell and failed to rot swiftly enough locked away carbon. Each locked layer nudged oxygen higher, and each shift in oxygen in turn changed the range of bodies possible. In this way, atmosphere is not a backdrop but a character, shaping evolution as surely as predators, competition, or climate. That is what makes this story more than an oddity about oversized bugs. It is a parable of interdependence. The chemistry of air and the architecture of life are written into each other, line for line, breath for breath. As we move through this ancient forest, you will come to see how these insects breathed without lungs, why they could stretch so large, and how their reign eventually narrowed again. But before we dwell on their decline, we linger first in their moment of grandeur, when the world's breath was deep enough to carry giants aloft. And so the question lingers. What can the rise of insects the size of birds teach us about the hidden partnership between life and the air it breathes? The day fades, and with it the Carboniferous world takes on a softer tone. The light slides down through the canopy of strange trees, filtering through giant fronds until it settles into a calm twilight that seems to stretch forever. This is not a forest of familiar species. Instead, it is a land ruled by lycopsids, scale trees that tower upwards with trunks patterned like woven fabric. Their roots do not dig deeply into the soil, but spread wide and shallow across the swamp floor, gripping mud that is as much water as it is land. Ferns and horsetail relatives fill the gaps, their stems jointed like a series of pipes, their leaves feathering out in brushy fans. The air clings close to the skin, thick with humidity, warm without being scorching, as if the whole world has been placed under a giant glass dome. The ground beneath is not solid but springy, cushioned with layer upon layer of fallen plant matter. Every step presses into peat that is destined, over millions of years, to harden into seams of coal. Pools of dark water lie everywhere, glassy and still until a ripple disturbs them. A frog-like amphibian slipping below, a dragonfly-like shadow hovering above, or perhaps just the release of a bubble from deep within the swamp. There is a constant hush, but not silence. The air carries the tiny sounds of a living forest, the flick of wings, the plop of an animal settling into the water, the creak of plants shifting in the moist breeze. As twilight deepens, the forest shows another secret. Along rotting logs and damp bark, faint glimmers appear. It is not the insects that glow here, but fungi. Modern eyes would call it foxfire, that gentle greenish light created by chemical reactions as fungi break down wood. In the deep past, just as now, bioluminescence may have been an accidental gift of metabolism, a side effect of how cells manage oxygen and reduce stress from reactive molecules. Yet in this dim Carboniferous forest, the result is enchanting, a subtle glow that makes each fallen log seem like it is storing a tiny shard of starlight. The faint shimmer plays tricks with shadows, softening the swamp's edges and lending the forest a dreamlike atmosphere. The heavy warmth of the evening is more than a comfort, it is a clue. The chemistry of the air itself is different here. Today, oxygen makes up about 1/5 of Earth's atmosphere, a balance struck over long ages. But in the Carboniferous period, oxygen rose to much higher levels, likely close to 1/3 of the atmosphere at certain peaks. Geochemical evidence points to this. Charcoal deposits are scattered through Carboniferous rocks, showing that fires burned easily. At such high oxygen concentrations, even damp wood could ignite with little encouragement. It was a world primed for flame, but it was also a world primed for life to breathe differently. Elevated oxygen reshaped possibility. Insects, unlike mammals, do not have lungs to pull air deep into their bodies. Instead, they rely on spiracles, tiny openings that connect to tracheae, a branching network of tubes that delivers oxygen directly to tissues. This system works beautifully at small sizes, but it begins to strain as bodies grow larger. Diffusion, the quiet spread of molecules from where they are abundant to where they are scarce, only works quickly over short distances. Larger animals risk longer delivery times, as oxygen takes longer to reach cells at the farthest edges. Yet when oxygen is more concentrated in the air outside, diffusion moves more forcefully. The gradient is steeper, and the distance oxygen can travel effectively is greater. This meant that, in a sense, the Carboniferous atmosphere opened new doors for insects. Where today's air would limit their maximum size, the richer oxygen of the time relaxed that barrier. Muscles could work harder before they ran short of fuel, and tracheal tubes could stretch their efficiency further. The higher oxygen made every wing beat and leg movement easier to sustain. It was not a magical solution to every problem of scale. Physics and body structure still had their say, but it tilted the balance. The forest was not just home to ordinary creatures scaled up, it was an environment that encouraged those scales to stretch further. Imagine the metabolism of these creatures as a fire burning inside a lantern. The brighter the flame, the more fuel it demands, and the more oxygen it must consume to keep glowing. For an insect trying to fly or hunt, those flames must burn hot and steady. In our current atmosphere, there is a natural limit to how much oxygen can be pulled in through those spiracles and tracheal tubes. But in a Carboniferous forest, where the air itself carried more oxygen, it was as if the flame had a more generous supply. The lantern could shine brighter, or last longer, or simply burn without strain. The atmosphere itself acted as an unseen ally. This gift of oxygen was not the work of chance alone. The swampy ecosystems played a major role in shaping it. Vast amounts of plant matter fell into bogs and did not fully decay. The conditions were waterlogged, acidic, and often poor in the microbes that would normally recycle carbon back into the air. Instead, the carbon was locked away, compressed over time into coal. With carbon dioxide pulled from the air and not returned quickly, oxygen levels climbed. Fires fed the balance, burning some of that oxygen away but never enough to undo the steady surplus created by the burial of plant matter. The result was an atmosphere richer in oxygen than at almost any other time in Earth's history. Walk through the forest at this twilight hour, and it becomes clear how atmosphere and ecology intertwined. Amphibians thrive along the edges of pools, their thin skins soaking in moisture and oxygen alike. Early reptiles take their first cautious steps into drier ground, protected by scales that keep their bodies from losing too much water. Insects dart and hover, their wings catching the thicker air with greater lift than today's skies provide. The very density of the air changes how creatures move, slowing sound, making each wing beat feel heavy yet powerful, and giving flight a kind of buoyant grace. The Carboniferous world breathes deeper, and everything in it responds. Fires burn more fiercely. Creatures that depend on diffusion can grow larger. Even the smallest life forms, the fungi glowing on fallen logs, adapt their chemistry to manage the stress of this oxygen-rich environment. This is what makes the setting more than just a swamp filled with strange plants. It is a living laboratory, a moment when atmosphere itself sculpted the limits of possibility. And within this hushed, humid twilight, with its faint green glows and heavy oxygen-rich air, the stage is set for a remarkable story. A story where wings span wider, legs stretch longer, and the boundaries of size bend in ways that today seem almost unbelievable. The forest may look quiet, but in every breath of its air, a new kind of life is waiting to take shape. Breathing, as humans know it, involves lungs that draw in air, blood that ferries oxygen, and a steady rhythm of inhale and exhale. Insects took a different path altogether. Their bodies are threaded with a remarkable network of tubes called tracheae, delicate passages that carry air directly from the outside world to the innermost cells. Instead of relying on red blood cells to deliver oxygen through circulation, insects let the air itself make the journey. This design is at once efficient and limiting, elegant in its simplicity yet bound by the quiet rules of physics. Along the flanks of an insect's body lie spiracles, tiny valved openings, each no larger than a pinprick. These are the doorways to the tracheal system. Air slips in through them, and once inside it travels down wider tracheal trunks that branch and branch again into ever finer tubes. The smallest of these, the tracheals, reach astonishing closeness to the tissues they serve, sometimes within a single micron of mitochondria, those cellular powerhouses where oxygen is burned for energy. With such intimacy, there is almost no delay. Oxygen is delivered right to the doorstep where it is needed most, and carbon dioxide exits by the same route, sliding back along the gradient to the world outside. Diffusion is the primary driver here. It is the simple spreading of molecules from high concentration to low concentration, like the way a drop of ink gradually unfurls in still water. Diffusion works quickly over short distances, but its efficiency plummets as distances grow longer. A molecule might cross a tiny gap in milliseconds, but increase that path tenfold and the time balloons by 100-fold. This is why insects are usually small. Their breathing system was built to serve bodies where no cell is too far from a tracheal tube. For a tiny ant, diffusion is a swift and faithful courier. For something the size of a crow, diffusion starts to look like a courier stuck in heavy traffic. Yet insects are not entirely at the mercy of diffusion's leisurely stroll. Many have evolved tricks to stir the air within their bodies. Some species rhythmically pump their abdomens, squeezing and releasing to push air along the tracheal highways. Others rely on air sacs, thin-walled expansions of the tracheae that collapse and inflate like quiet bellows, drawing air deeper into the system. Even wing beats can help, as the thorax flexes and shifts with each stroke, creating tiny pulses that drive air toward oxygen-hungry flight muscles. This convective ventilation adds a second layer to the breathing design. Diffusion carries oxygen across the smallest distances, while rhythmic movements provide bulk flow to refresh the system. Despite these clever solutions, a fundamental problem remains: the balance of surface area to volume. As an insect grows larger, its volume, the total tissue needing oxygen, increases much faster than its surface area, or the relative capacity of its tracheal openings. A creature twice as wide has 8 times the volume, but only 4 times the surface area. In practical terms, that means oxygen demand rises far faster than the ability to supply it. It is like expanding a city's population without adding new roads. Soon, the traffic overwhelms the network. Larger insects must devote more of their internal space to tracheae, sacrificing room that could otherwise be used for muscle, gut, or reproductive organs. The scaling law becomes a stern reminder that there are limits to how big a purely diffusion-based system can comfortably grow. This is where the atmosphere of the Carboniferous period played such a decisive role. When oxygen outside was richer, the gradient driving diffusion inside the tracheal system grew steeper. The same hallways suddenly carried a heavier stream of oxygen with less resistance. The bottleneck of distance eased. Where today's insects might bump into size limits, their ancient relatives found those barriers softened. It was as if the library of tracheae had its corridors widened and its shelves stocked more generously, allowing information to flow further and faster. With oxygen levels higher, insects could grow larger without suffocating their own tissues. It is worth pausing to notice the elegance of this arrangement. Insects never needed blood hemoglobin to carry oxygen. They never evolved tiny couriers patrolling their bloodstream. Instead, they invested in architecture, tubes that lace every part of the body with direct access to the air. In small species, this design outcompetes any lung and blood-based system in terms of efficiency. For larger species, it creates constraints, but with higher atmospheric oxygen, those constraints loosened. The griffin flies that once skimmed across ancient swamps could not have existed in today's air. Their tracheae would have struggled to deliver enough oxygen to power long wings. But in a Carboniferous atmosphere with oxygen near 1/3 of the mix, the gradient supplied them with what they needed. Insects also face trade-offs that come with this design. Spiracles are potential leaks for water, and in hot or dry conditions, evaporation can be deadly. To counter this, many insects can shut their spiracles tightly, sometimes for minutes at a time, opening them only when necessary. Some even employ a breathing rhythm known as discontinuous gas exchange, holding spiracles closed, then briefly opening them in bursts that release carbon dioxide and draw in oxygen. This behavior conserves water while maintaining metabolic balance. It shows that even the simplest seeming systems come with layers of adaptation, tuned to fit a wide range of environments. The design also intertwines with activity levels. Insects at rest often rely entirely on diffusion, a calm flow of oxygen down the tracheae. During intense activity, chasing prey, escaping predators, or flying, convection takes over, with air sacs and body movements helping to refresh the system. Think of it as a 2-speed breathing system, quiet and efficient for stillness, rhythmic and forceful for action. Few other animals enjoy such flexibility at such a small scale, and it is one of the reasons insects thrive in nearly every corner of the planet. Yet even flexibility cannot rewrite the physics of scaling. For any creature relying primarily on diffusion, size carries unavoidable costs. This is why the Carboniferous oxygen boost was so transformative. With every breath, insects could stretch those limits a little further. Wings could beat longer before fatigue, legs could carry heavier frames, and body sizes that today seem impossible could not only exist but flourish. The world itself had, in effect, adjusted the rulebook, allowing organisms to experiment with forms that later ages could no longer support. Picture once again those tracheae, shining like silver threads under the cuticle, weaving through the body like corridors in a vast library. In normal air, the hallways are narrow and crowded, every molecule jostling to reach its destination. In an oxygen-rich Carboniferous atmosphere, it was as though the walls were pushed outward, doubling the space, and the shelves were restocked with richer supplies. Information, oxygen, could move quickly to every reader, cell, without the usual bottlenecks. The library could grow larger, and still the conversation carried on smoothly. The insect breathing system is one of nature's great lessons in directness. It is at once simple and profound. No middlemen, no complex pumps, just a network of airways connected to the outside world. Its beauty lies in its closeness. Oxygen does not travel across long winding detours, but walks straight in through the front door. Its limitation lies in the same simplicity, for diffusion can only stretch so far before it falters. In the Carboniferous world, the very air lent a helping hand, and the boundaries shifted just enough for giants with 6 legs and enormous wings to step onto the stage. What remains is a reminder that the breath of life is not just about lungs or blood, but about physics, chemistry, and opportunity. Insects found a solution that served them well, and when the atmosphere tilted in their favour, that same solution allowed them to grow into creatures that would tower over the insects we know today. It was not magic, but mathematics of air and body played out in the quiet corridors of tracheae, widened by the generosity of an atmosphere richer than our own. The idea that insects once grew to giant sizes is not just a tale from the imagination. The evidence lies in the chemistry of rocks, the patterns of fire, and the fossils themselves. To understand how it happened, it helps to start with something as simple as oxygen, the quiet gas that makes both fire and life possible. Today, Earth's atmosphere contains about 21% oxygen. In the Carboniferous period, more than 300 million years ago, that number climbed much higher, in some intervals reaching close to 35%. That difference might sound modest, but in the world of biology it is transformative. Scientists piece this picture together through indirect clues, because there are no ancient air samples sitting neatly in bottles. One line of evidence comes from charcoal deposits. Fire needs oxygen, and the frequency of ancient wildfires leaves behind telltale layers of carbonized plant matter. In Carboniferous rocks, charcoal is surprisingly abundant. Laboratory experiments show that sustained wildfire requires oxygen above about 17%, and when oxygen climbs into the 30s, even damp vegetation can ignite. The fossil record of constant fire during this time suggests oxygen was indeed elevated, and not just for a brief moment, but for millions of years. Other clues come from isotopes preserved in ancient soils and sediments. Ratios of carbon and sulfur isotopes reflect how much organic material was buried without decaying, and how that burial influenced atmospheric balance. During the Carboniferous, vast amounts of plant matter were locked away in swamps that slowed decomposition, eventually forming thick seams of coal. Every tree that fell and failed to rot meant more carbon trapped underground and more oxygen left circulating in the air. The coal measures of Europe, North America, and Asia are geological monuments to this imbalance, a reminder that forests shaped atmosphere as much as atmosphere shaped forests. With an atmosphere carrying so much oxygen, insects found themselves in a unique position. Their tracheal breathing system, while elegant imposes limits. Oxygen must diffuse through tubes to reach every cell. In today's air, those limits keep insect bodies relatively small because diffusion slows dramatically as distances lengthen. In an oxygen-rich world, diffusion works over greater ranges, and every breath delivers more molecules per second. That means the same system suddenly supports larger bodies and more vigorous activity. Think of it as an invisible upgrade to the plumbing. Tracheae that once carried oxygen just far enough now delivered it with room to spare. The gradient of oxygen concentration between the air and the tissues was steeper, so molecules moved more quickly into the body. Larger insects could afford the long pathways, and flight muscles could burn energy at a higher rate without gasping for fuel. Insects did not need new machinery. They only needed the air itself to change. To borrow a light-hearted comparison, it was as if the Carboniferous gym required no membership. The atmosphere simply did more of the lifting for them. The results were spectacular. Dragonfly-like griffin flies spread wings more than 1/2 meter across, patrolling swamps with silent authority. Millipede relatives known as Arthropleura stretched over 2 meters in length, weaving through fallen trunks like living trains of armor. Even the more ordinary insects of the time reached sizes that would look startling today. What we see in fossils is not a fantasy of evolution gone wild, but the natural extension of biological rules given a new set of conditions. Yet oxygen alone does not write the whole story. Other factors also nudged body size upwards. Climate was one of them. The Carboniferous world was warm, humid and relatively stable, conditions that provided abundant plant matter and steady food webs. Abundance matters. A larger body is only an advantage if there is enough food to fuel it. With forests covering vast regions, the buffet was generous. Predator-prey relationships also influenced the equation. Insects of the time faced fewer aerial vertebrate predators, since birds and bats would not evolve for hundreds of millions of years. Without those specialized hunters chasing them, large flyers had more ecological space to thrive. On the ground, amphibians and early reptiles did apply pressure, but the balance of threats was different than in later ages. The absence of certain predators meant that size, at least for some species, was more sustainable. Life history traits added their own influence. Some insects that grew large may have had slower growth cycles or longer lifespans, strategies made possible by stable environments. Others might have capitalized on niches created by the dense forests and abundant detritus. When resources are plentiful and competition takes different forms, evolution can experiment more broadly with body plans. It is also important to note that not every insect in the Carboniferous was a giant. The forest was still filled with small beetle-like creatures, delicate flies, and many species only a few millimeters long. Just as today, size diversity was vast, with giants occupying certain roles while smaller species thrived in others. Oxygen opened the door to larger bodies, but ecological dynamics decided who walked through it. The relationship between oxygen and body size has even been tested experimentally with modern insects. Studies have raised insects in atmospheres richer in oxygen and found that, in many cases, they do grow larger. Likewise, reducing oxygen often produces smaller individuals. These laboratory results do not mimic every detail of deep time, but they lend support to the idea that atmospheric chemistry plays a strong role in setting size boundaries. Still, the rise of giants was not permanent. The Carboniferous eventually gave way to the Permian period, and oxygen levels declined toward modern values. As the gradient eased, the advantages of large body size diminished, and the costs of carrying heavy frames grew sharper. Over evolutionary time, giant insects retreated, replaced by forms more in line with the atmosphere that followed. The brief experiment with gigantism ended, leaving only fossils as evidence. This does not diminish the significance of what happened. Instead, it highlights the profound connection between air and life. The size of an insect wing or the length of a millipede's body is not dictated by genes alone, but by the chemistry of the sky above. Oxygen concentration is a lever, and when it is pulled one way, giants emerge. When it shifts back, they vanish. Few other traits in evolution demonstrate so clearly the interdependence of biology and atmosphere. The Carboniferous was, in many ways, a grand ecological negotiation. Forests buried carbon, raising oxygen. Fires burned brighter, shaping landscapes. Insects stretched their bodies to new limits, carried by diffusion that worked more generously than ever before. It was a time when physics, chemistry and biology aligned to produce creatures that now seem improbable, but were once entirely ordinary. The evidence sits quietly in rocks and coals, in patterns of ancient charcoal and isotopic signatures. Taken together, they tell us that oxygen was the unseen architect of these giants. Not the only architect, but a critical one. Insects, with their tracheal networks, were especially poised to take advantage of it. The world breathed more deeply, and insects answered by growing larger, flying higher, and leaving us fossils that continue to astonish. What emerges from this chapter is a simple truth with far-reaching meaning. Life is not built in isolation. It is shaped moment by the chemistry of its surroundings. In the Carboniferous, the air itself gave insects permission to defy the size limits we know today. It is a reminder that the invisible gases we breathe are more than background. They are co-authors in the long story of life on Earth. The Carboniferous forests were unlike anything alive today. Step into one and the first impression is of height and repetition. The dominant trees were not pines or oaks but leucopsids, relatives of club mosses that in the modern world barely reach ankle level. Here, though, their descendants towered. Lepidodendron and Sigillaria grew up to 30 metres tall, their trunks patterned with diamond scars where leaves had once attached. Instead of spreading crowns, these trees often carried fronds at the top like bristling brushes, turning the canopy into a patchwork of green tufts against the humid sky. Among them grew vast horsetails, relatives of Equisetum, the kind of plant you might see today only as small reeds by a stream bank. Back then, some horsetail species were thicker than a human thigh and stood as tall as a 2-story building. Their jointed stems stacked like segments of bamboo, and their brushy tops multiplied until they resembled great green bottle brushes. Seed ferns added variety, fanning wide leaves from woody stems, contributing both shade and fallen litter. These three groups, leucopsids, horsetails and seed ferns, built an architecture that defined the Carboniferous world, one that was lush, damp and strange. Life in these forests moved to a slow rhythm. The climate was warm and consistently humid, with rainfall feeding endless swamps. Floodplains spread out like soggy carpets, and water often pooled where trees fell or streams shifted course. The ground was not firm soil but peat, thick mats of plant material accumulating faster than it could rot. Each season dropped layers of fronds, branches and trunks onto the forest floor. Instead of disappearing quickly, as leaves do in a modern oak forest, much of this material lingered, waterlogged and half-decayed. Over centuries it built up into peat beds meters deep, and with burial and time, these would compress into the coal seams that powered the Industrial Revolution hundreds of millions of years later. The slow cycles of wet and dry played a crucial role. During wet phases, swamps expanded and new peat layers formed. When drier intervals arrived, fires became common, igniting in oxygen-rich air and leaving behind sheets of charcoal. These alternating rhythms wrote a layered history: peat, then ash, then peat again. Each layer recorded not just plant growth but the chemistry of the atmosphere and the dynamic balance between burial and burning. The forests, in a way, became engineers of the Earth's future, storing vast amounts of carbon that would one day re-enter the sky when humans learned to dig it up. The question arises, why did so much carbon remain buried instead of returning to the air through decay? The answer lies partly in the microbes, or rather, the absence of certain ones. Fungi that could efficiently decompose lignin, the tough compound that stiffens wood, had not yet fully evolved in the early Carboniferous. As a result, trunks and branches were more resistant to breakdown than they would be today. Instead of vanishing into soil within a few years, they lingered, saturating wetlands with debris. Combined with waterlogging, which restricts oxygen and slows microbial activity, the result was a world where decay could not keep up with productivity. Plants captured carbon dioxide from the air, built immense forests, and when those forests died, their remains stayed locked away in the ground. Oxygen rose while carbon dioxide fell, reshaping the planet's atmosphere. The ecological roles of insects within this system were already diverse. Detritivores were everywhere, feeding on fallen plant matter and fungi. Millipede-like arthropods grazed across decaying litter, breaking it into smaller pieces that microbes could eventually process. Small beetle ancestors and early cockroach relatives scuttled through the peat layers, nibbling on softer tissues. These creatures did not eliminate the backlog of debris, but they contributed to the slow churn of organic material at the swamp's surface. Herbivory also began to leave its mark. By the late Carboniferous, insects had evolved mouthparts capable of chewing plant tissue, piercing stems, and scraping leaves. Fossil leaves from this era show distinctive damage, holes, skeletonized patches, and bite marks that speak of hungry mandibles at work. Some early orthopterans, the lineage that would later include grasshoppers and crickets, fed on fronds, while other groups may have mined within leaves or bored into stems. Though not as specialized as the insect herbivores of later ages, they were beginning to shape plant evolution through pressure and persistence. Predation completed the picture. Large griffin flies with wingspans wider than a dinner plate hunted other insects on the wing, their compound eyes scanning the swamp for movement. Smaller predators waited among the foliage, springing on unsuspecting prey. Even aquatic environments within the forest supported insect larvae with predatory habits, using strong jaws to seize invertebrates in the water. The food web was layered and complex, linking the oxygen-rich air above with the dark, still pools below. Every roll tied back into the peculiar chemistry of the swamp. Detritivores helped fragment plant matter, but could not finish the job without efficient decomposers. Herbivores trimmed leaves and stems, but were only a small dent in the flood of photosynthesis. Predators fed on other insects, recycling nutrients within the web but not removing carbon from the system. The net effect was accumulation. Plants grew faster than they could be broken down, and the backlog piled higher each year. The imbalance was not permanent. Later fungi and ecosystems would catch up. But for millions of years, Earth lived in a state where burial outweighed return. The forests themselves were dynamic, not static. Scale trees raced upward quickly, sometimes living only a few decades before collapsing. They invested less in wood and more in reaching sunlight fast, a strategy that made them vulnerable to toppling in storms or floods. Horsetails spread aggressively across open ground, stabilizing banks with mats of rhizomes. Seed ferns colonized gaps, their wide fronds spreading shade and reducing competition beneath. This constant turnover created a patchwork landscape, with open pools, dense stands of trees, and decaying clearings all existing side by side. Insects exploited every niche, from hovering above the water to burrowing into rotting logs. It is easy to picture these forests as primeval and alien, yet they were also the foundation for many features of the modern world. They altered atmospheric balance, created coal deposits, and hosted ecosystems with recognizable roles: decomposers, herbivores, predators, already interacting in ways that echo today's forests. The difference lay in the details, the sheer scale of the plants, the inefficiency of decay, and the higher oxygen that allowed insects to stretch their bodies beyond the limits familiar to us. Walk through a Carboniferous swamp in your mind and the sensations pile up. The air is thick and warm, heavy with the smell of damp vegetation. Towers of leucopsids rise like columns, their patterned bark catching the low light. Ferns brush against your legs, and horsetails rattle gently in the breeze. Underfoot the ground yields, spongy with peat that preserves the ghosts of countless seasons. Amphibians stir along the banks, and overhead a shadow passes, wings broad, body slender, eyes gleaming in the fading light. Somewhere nearby, fungi glow faintly along a fallen trunk, a soft green light against the dark. This is a world where atmosphere and forest are locked in dialogue, each shaping the other in ways that will ripple into deep time. The coal forests were not just ecosystems, they were machines for rewriting the planet. Their rhythms of growth and decay set the stage for the age of giant insects, fueled by oxygen rising higher than at almost any other point in Earth's history. But beyond their role in insect evolution, they left a legacy still with us today. The coal seams that powered human industry, the oxygen record etched in rock, and the reminder that even the tallest trees rest on unseen feedbacks between life and atmosphere. In the Carboniferous twilight, surrounded by leucopsid giants and the soft glow of fungi, one can sense that these forests were not only alive in their own moment, but were quietly building the future. Among the most striking figures to glide through the Carboniferous skies were the griffin flies, led by the genus Meganeura. With wingspans stretching close to 70 centimeters, they were among the largest insects ever to take flight. To the eye, they would have looked like enormous dragonflies. 4 slender wings veined like stained glass, a long narrow abdomen trailing behind, and huge compound eyes reflecting the swamp's dim light. Yet despite their resemblance, griffin flies were not true dragonflies. They belonged to an extinct order of insect relatives, the Meganisoptera, which shared some similarities with dragonflies and damselflies, but stood apart in lineage. For millions of years they were the undisputed rulers of the air. To understand how they managed this feat, it helps to picture their wings in detail. Each was a marvel of natural engineering, thin membranes stretched across a framework of veins that carried both strength and flexibility. The veins created a lattice that resisted tearing while allowing subtle twists and adjustments during flight. 4 wings meant not just redundancy, but versatility. By moving them in slightly different phases, griffin flies could hover, glide, and dart with a precision that even modern aircraft would admire. Their thorax, the central engine of the insect body, was packed with powerful muscles anchored to the wing bases. These indirect flight muscles did not tug the wings directly, but flexed the thoracic box itself, causing the wings to beat in rapid, efficient strokes. The atmosphere of the Carboniferous was particularly kind to such flyers. Denser, more oxygen-rich air meant that lift came more readily. A broad wing moving through this heavier medium generated more support for the insect's body. For Meganeura, this was a crucial advantage. Their size would have been difficult to sustain under today's thinner air, but in the ancient sky they found conditions that matched their design. Every wing beat was aided by physics, as if the air itself had decided to lend a hand. In flight, a griffin fly would have been a patient hunter. With eyes that dominated its head, each made up of thousands of tiny facets, Meganeura could detect the slightest flicker of movement across the swamp. The compound eyes granted an almost panoramic view, ideal for spotting prey in dim light or amid dense foliage. Once prey was located, perhaps a smaller insect rising from the peat, or a juvenile amphibian stirring near the water's edge, the griffin fly would swoop silently, legs outstretched. These legs, spined and angled forward, formed a basket mid-air, a perfect trap for seizing struggling prey. Caught in this net of spines, the victim had little chance of escape. The griffin fly would then settle onto a perch, perhaps the trunk of a leucopsid tree or a broad frond, to consume its meal with strong mandibles. The hunting style was one of efficiency rather than drama. There was no need for speed records or endless chases. The combination of excellent vision, quiet wings, and sharp reflexes made Meganeura a predator that succeeded by being unhurried but accurate. In the still air of the Carboniferous evening, the flutter of its wings might have been the only warning that something large and watchful was near. Imagine sitting by a swamp pool and seeing a shadow the size of a raven glide silently across the surface, only to vanish again into the green dusk. Fossils provide the evidence for these remarkable insects, though no living creature matches their scale. The wings are often preserved as impressions in fine sediments, their delicate vein patterns etched into stone. These patterns allow scientists to reconstruct the overall shape of the wing and estimate the wingspan. The largest specimens of Meganeura show wings more than 30 centimeters long each, confirming the creature's enormous size. Fossils of the body are rarer, but enough fragments exist to piece together the proportions: long, narrow abdomens, robust thoraxes, and heads dominated by bulging eyes. By comparing these fossils with modern relatives, entomologists infer lifestyle and capabilities. Dragonflies today, though smaller, are agile hunters with similar wing structures, capable of catching prey mid-air with startling accuracy. It is reasonable to suggest that Meganeura behaved in much the same way, scaled up to take advantage of its environment. The details of wing vein arrangements also suggest strong, versatile flyers rather than clumsy gliders. These were not fragile insects blown about by the wind. They were active predators commanding their skies. The very existence of such creatures highlights the interplay between biology and environment. Insects breathe through tracheal tubes that limit how large they can grow under ordinary conditions. With oxygen levels higher, those limits shifted. The muscles in Meganeura's thorax could burn fuel at a rate that sustained powerful wing beats, and the dense air gave the wings the lift needed to carry a large frame. Without that combination of atmospheric chemistry and biomechanical design, a griffin fly would never have lifted off the ground. In imagining them, it is tempting to picture danger, but their role was not monstrous. They were predators of smaller insects and perhaps occasional tiny vertebrates, nothing more. To an amphibian, or a smaller arthropod, a griffin fly's approach might have been intimidating, but to a human observer, it would have been wondrous more than frightening. Their presence added another layer to the already complex ecosystems of the coal forests, balancing populations of insects in the air, the way amphibians and reptiles did on the ground. Scientists continue to debate some details. Could Meganeura truly sustain flight with such large bodies, or were they limited to short bursts? The fossil record alone cannot provide a complete answer, but the consensus leans toward active flight, given their robust wing structures and powerful thoraces. Experiments with models suggest that the denser air of the Carboniferous would indeed have supported such flight. While uncertainties remain, the idea of a giant griffin fly calmly patrolling the swamp fits both the fossil evidence and the physics of the time. There is also the question of why no insects today approach such sizes. Part of the answer lies in the atmosphere, which no longer carries the same oxygen richness. Part lies in ecology, as birds and bats dominate aerial predation niches that insects once held uncontested. Meganeura flourished in a world uniquely suited to it, and when that world changed, its lineage faded away. The fossils remain as reminders of that brief window when insects claim the skies in forms that dwarf their modern descendants. In the imagination, it is easy to watch one glide over the still water of a Carboniferous swamp. Its wings tilt slightly, catching the dense air in a graceful turn. The body steadies, the compound eyes fix on a movement below, and then, with a sudden dart, the legs close around a smaller insect. A brief pause, a quiet landing on a frond, and the meal is gone. The swamp returns to its hush, but the echo of those wide wings remains. Meganeura and its relatives were not merely curiosities of size. They were proof of what life can do when given a favourable atmosphere, an open sky, and time to refine the mechanics of flight. With delicate veins of stone as our evidence, we know that once, long before birds, long before bats, the masters of the air were insects with wings like panes of glass, and eyes that watched the Carboniferous dusk with endless patience. Across the damp floor of the Carboniferous forest, a shape moves slowly but steadily, long as a dining table and armoured like a living train. This was Arthropleura, a millipede relative that grew into the undisputed giant of the land in its time. Estimates based on fossil remains and trackways suggest individuals could reach lengths of over 2.5 metres and widths close to 0.5 metre. Imagine a centipede or millipede scaled up to the size of a small car, with dozens of legs rippling in synchrony, carrying a segmented body across the swampy ground. For millions of years, Arthropleura held the title of largest known land invertebrate. Much of what we know about it comes not from complete skeletons, but from trace fossils, its footprints. Across what are now sandstone beds in Europe and North America, enormous trackways reveal the creature's passage. Parallel rows of impressions mark the placement of legs, while central drags show where the abdomen brushed against the ground. Some tracks stretch for meters in length, the careful, deliberate steps preserved in fine sediment, as though the animal had just passed by. The width of these trackways confirms that this was not a modest millipede enlarged in the imagination. These were titans that left undeniable marks in their landscapes. Despite its daunting size, Arthropleura was not a predator. Fossil evidence points toward a diet of plants and decaying organic matter. It likely grazed among the detritus of the swamp floor, consuming fallen leaves, soft stems, and fragments of rotting wood. Its jaws were adapted for chewing rather than slicing flesh, and its role in the ecosystem was that of a recycler. By breaking down plant material into smaller pieces, Arthropleura helped return nutrients to the soil, supporting the cycling of energy within the forest. In this sense, it played a role similar to modern millipedes and woodlice, though on a much grander scale. Its preferred habitat was the coal forests themselves, humid, sheltered, and filled with an endless supply of decaying plant matter. The dense canopy and frequent floods created an environment where detritus piled up faster than it could decompose, leaving a buffet for decomposers large and small. Arthropleura thrived in this niche, lumbering through the undergrowth in search of fresh deposits of litter. It likely avoided deep water, sticking to damp ground where its many legs found firm purchase. Yet its trackways show it was capable of long journeys, crossing floodplains and navigating the uneven terrain of fallen trunks and tangled roots. But size brings burdens as well as benefits. An exoskeleton provides armour and structure, but it does not scale up gracefully. As arthropods grow larger, their protective shells become heavier, and the strength needed to support them increases disproportionately. For Arthropleura, this meant its body had to be carefully engineered to distribute weight across many legs, each one lifting only a small fraction of the whole. Its segmented armour gave flexibility, but each segment carried plates that had to be shed and replaced during molting. Molting at such a size must have been one of the most dangerous moments in its life. Like all arthropods, Arthropleura periodically shed its exoskeleton to grow. At this stage, the old armour split and the animal wriggled free, leaving behind a ghostly shell. For a creature over 2 meters long, this process would have taken time and left it vulnerable. Until the new exoskeleton hardened, it was soft, defenseless, and unable to move with confidence. In the relative safety of the Carboniferous, where large terrestrial predators were scarce, this risk may have been manageable. Even so, it was a reminder that gigantism came at a cost. The structural limits of its body also shaped how it moved. Arthropleura did not scuttle quickly like a small centipede. Its many legs moved in waves, each segment lifting and setting down in sequence, creating a rolling ripple along its flanks. The overall effect was a deliberate, steady pace, more ponderous than frantic. This gait, preserved in trackways, suggests an animal that relied on mass and persistence rather than agility. It was large enough to brush aside smaller obstacles and stable enough to cross uneven ground without toppling. Yet even so, it would have had to negotiate carefully around the towering roots and fallen trunks of the forest. Imagine one such crossing in detail. A lycopsid has fallen across the forest floor, its trunk thick as a modern telephone pole and slick with moss. Arthropleura approaches, antennae probing ahead. It lifts the front half of its body, arches over the obstacle and plants its foremost legs on the opposite side. The rest of the body follows in a measured wave, each segment rising and settling in turn. Dozens of legs grip the surface, distributing weight evenly until the great creature is safely across. For a moment it seems to pause, antennae moving slowly as though tasting the humid air, before continuing on its quiet journey through the undergrowth. In its own time, Arthropleura was not an oddity, but a natural extension of the environment. Elevated oxygen made such size possible, while abundant plant matter provided endless fuel. The scarcity of large land predators allowed it to move with relative security, yet like Meganeura, it was ultimately a product of conditions that would not last. As oxygen levels dropped and new vertebrate predators diversified, the advantages of gigantism diminished. The lineage eventually disappeared, leaving only its footprints and occasional body fragments in stone. Still, the traces speak volumes. They tell us that once, long before mammals or dinosaurs, the forest floor was patrolled by creatures that defy modern expectations of what an arthropod could be. They show that size, though constrained by physics and biology, can be stretched when the environment offers the right combination of support and opportunity. And they remind us that ecosystems are not just built by predators or towering trees, but also by the quiet recyclers that keep energy moving through the system. To picture Arthropleura today is to imagine an encounter both awe-inspiring and oddly peaceful. A creature vast by insect and millipede standards, yet harmless, trundling through the swamp with patient strides. It leaves behind a trail of orderly footprints, as if writing its presence into the mud for future eyes to discover. The forest closes behind it, shadows fold over its track, and it vanishes once more into the rhythm of the Carboniferous. To imagine life as a giant insect or arthropod is to imagine life inside a suit of armour, an exoskeleton that both enables and constrains everything the creature does. Unlike vertebrates, which grow around an internal scaffold of bone, arthropods carry their skeleton on the outside, a hardened shield that doubles as both protection and support. It is a remarkable system, built from chitin, proteins, and sometimes reinforced with minerals, all layered into a composite material strong enough to ward off attacks, yet flexible enough to bend at the joints. It is as though nature perfected a lightweight chainmail, one that grows around its wearer and locks them safely inside. At the microscopic level, this armour is more than just a shell. The exoskeleton is made up of layers, called the cuticle, each with a different role. The outer epicuticle is waxy and waterproof, keeping moisture sealed inside, a crucial defence in an environment where dehydration could be fatal. Beneath that lies the exocuticle, the hardened portion that provides rigidity and strength. At the base is the endocuticle, which retains more flexibility, giving joints and softer segments their bend. Together, these layers act like the different plies of a high-tech composite, balancing toughness, resilience, and function. This design works beautifully for small creatures. A beetle can scuttle about in its armour without issue, a mantis can strike with spined forelegs, and a dragonfly can flex its thorax mid-flight without cracking. But as scale increases, the physics of the situation shifts. The strength of the exoskeleton depends on its thickness relative to size, and as an arthropod grows larger, the weight of its armour increases faster than the area available to support it. What was once light protection becomes a heavy burden. For a creature like Arthropleura, spanning over 2 meters, the cost of carrying its armour would have been immense. Each step meant moving not just muscle and tissue, but a layered shell that could easily weigh as much as the soft body inside. The challenge of scaling is made clearer by considering surface area versus volume. Volume increases with the cube of length, while surface area only increases with the square. That means as an arthropod gets larger, its body mass grows faster than the surface area of its exoskeleton. To compensate, the armour has to thicken disproportionately, and that added thickness piles on yet more weight. It is a cycle of diminishing returns, where growth demands heavier armour, and heavier armour demands more muscle power to move. But muscle power is limited by oxygen delivery and biomechanical constraints. It is a wonder, really, that some arthropods managed to push these limits as far as they did. And then comes the most precarious moment of all, molting. Unlike bones, which expand as the body grows, an exoskeleton is fixed once hardened. To grow larger, an arthropod must shed the old shell entirely and replace it with a new one. The process begins with enzymes that separate the body from its rigid case, dissolving parts of the old cuticle. The animal then swells with air or water, splitting its shell along predetermined seams. With laborious effort, it wriggles free, pulling dozens or even hundreds of legs from their tight sockets. At this stage, the arthropod is at its most vulnerable. Its new exoskeleton is soft and pale, unable to provide protection or support. The animal often hides, remaining still until the new cuticle hardens and darkens. For something the size of Arthropleura, this was no small risk. A molting cycle might leave it exposed for hours or even days, a lumbering giant with no armour, trusting that its sheer size and the lack of major predators on land would keep it safe. Smaller insects might molt hidden under bark or soil, but a creature over 2 meters long had fewer options. It simply had to endure. Molting also comes in steps, not gradual increments. Growth is episodic, happening in sudden leaps. An insect does not gain a little size each day. It remains the same until its next molt, and then, quite suddenly, it emerges larger. This rhythm of life means each molt is both a rebirth and a gamble. A successful molt leads to a stronger, more capable creature, but a failed molt, where the insect cannot fully shed its old shell, can mean death. It is as if every upgrade to the armour came with a chance of catastrophic malfunction. The trade-offs of an exoskeleton extend beyond growth. Armour provides protection against physical damage and predation, but it comes at the cost of mobility. A heavily armoured beetle cannot dart as swiftly as a nimble fly. A thick-shelled crab is not built for speed on land. Every arthropod balances this equation differently depending on its niche. For Carboniferous giants, the choice leaned toward protection and stability. A bulky shell limited agility, but in a world with few threats on land, stability and resilience were more valuable than rapid movement. Think of it like wearing a suit of medieval plate armour made of living tissue. It is undeniably protective, but running a sprint or leaping hurdles becomes almost impossible. And unlike a knight who can set aside the armour at day's end, an arthropod lives inside its armour continuously. The suit is its skin, its skeleton, and its shield, all in one, and every so often that suit must be abandoned and rebuilt, piece by piece at great personal risk. There is elegance in this design despite the hazards. Chitin, the building block of exoskeletons, is one of nature's most versatile molecules. It is lightweight yet strong, and in combination with proteins and sometimes calcium carbonate, it can form materials ranging from the hardness of a beetle's shell to the translucence of a butterfly's wing. Modern engineers study chitin for inspiration in designing composites, marvelling that such a simple sugar-based polymer can be spun into so many forms. In the Carboniferous, this material allowed arthropods to experiment with size, pushing their biology to the limits of physics and atmosphere. The existence of giant arthropods shows that, under the right conditions, even the burdens of an exoskeleton can be overcome. Elevated oxygen levels reduced metabolic constraints, plentiful food supported larger bodies, and a relatively predator-light environment gave room for experimentation. For a time, the armour of giants did not hold them back but allowed them to dominate. Yet the very design that gave them strength also sowed the seeds of their eventual limitation. When conditions changed, the demands of molting, scaling and armour became insurmountable. Still, there is something captivating about the image. A creature clad in natural composite armour, reshaping itself in cycles, living a life dictated by physics as much as by ecology. It is a reminder that every adaptation carries trade-offs, and even the most extraordinary design is a negotiation between possibilities and limits. Wearing a suit of nature's composite armour that must be rebuilt on schedule, arthropods walk the line between protection and constraint, and for a time, they walked it as giants. To understand how a creature like Meganeura could sail through ancient skies, it helps to first picture the air itself. The Carboniferous atmosphere was not only richer in oxygen, but also denser overall, with slightly higher pressure than today. That density changes the rules of flight. Lift, the upward force that keeps wings aloft, depends on the density of the air, the speed of the wing, and the surface area of the wing itself. Denser air means more molecules brushing against the wing surface, which in turn makes it easier to generate lift. In other words, the very sky offered a little extra support to creatures daring enough to rise into it. Think about how swimming feels in water compared to moving your arms in air. Water resists you more, providing extra push for each stroke. Denser air in the Carboniferous played a similar role for flying insects. They didn't have to flap as frantically to stay airborne. The environment itself helped carry them. This gave giant winged insects like griffin flies the freedom to expand their wingspans beyond what would be practical today. Their broad, lace-like wings caught not just the air currents, but the enhanced buoyancy of a sky packed with molecules. Still, physics sets boundaries. For an insect, flight is a matter of balancing power output with aerodynamic demands. The muscles in the thorax drive the wings up and down, often at astonishing speeds in smaller species. Modern mosquitoes may flap hundreds of times per second. Larger insects, however, must flap more slowly, as their wings are bigger and heavier. In a denser atmosphere, this slower beat still provided sufficient lift. The griffinfly's wings could sweep through the sky at a relatively gentle frequency, trading frenetic buzzing for steady, powerful strokes. Wing loading, the ratio of body weight to wing area, is another key factor. A hawk has relatively high wing loading compared to an albatross, which explains why the albatross is built for effortless gliding across oceans, while the hawk relies on bursts of power. For Carboniferous giants, low wing loading was crucial. Broad wings distributed their weight over a wide surface, making sustained flight feasible. In denser air, the threshold for effective wing loading shifted even further in their favour. A creature like Meganeura, with a wingspan over 60 centimetres, could glide on air currents that might barely budge a modern dragonfly. Yet more air density also meant more drag. Every time a wing moved, the insect had to push against thicker resistance. There is a balance here. Denser air aids lift, but demands more muscle power to overcome drag. The advantage was real, but not limitless. Too much density would hinder rather than help. The Carboniferous atmosphere provided a sweet spot. A sky heavy enough to carry large wings, yet light enough to allow manoeuvrability. One of the most striking advantages of denser air was its effect on gliding potential. Imagine a griffinfly perched on a towering lycopsid, launching into the evening sky. With wings extended, it could catch rising thermals spiralling slowly upward. Each broad stroke would carry it farther with less effort, like a paper airplane gliding longer in thicker air. Modern dragonflies can glide briefly, but Meganeura likely excelled at it, spending stretches of time simply coasting. To picture it is to see a living kite, borne aloft over swamps and fern thickets. Flapping frequency and muscle design worked in tandem with this environment. Unlike birds with their single pair of wings, insects often operate two pairs that may move independently or in sync depending on the species. In the case of griffinflies, the paired wings could work together to provide both power and stability. Denser air smoothed this motion, allowing steady flight rather than erratic fluttering. In effect, the atmosphere gave them more leeway, reducing the precision needed in every motion. It is tempting to imagine them as clumsy simply because of their size, but that would be unfair. Their wings, with intricate venation, were not just flimsy membranes, but sophisticated aerodynamic structures. The veins acted like spars in a sail, controlling flex and preventing collapse mid-beat. In a denser sky, these features would have made each wing stroke efficient, turning muscular effort into sustained flight. The result was not an ungainly giant, but a capable aerial hunter. There is also the matter of energy. Sustained flight is costly and oxygen fuels the fire. Here again, the Carboniferous offered an advantage. With elevated oxygen levels, the tracheal system of these insects could deliver more to their muscles than would be possible in today's atmosphere. Denser air carried their wings. Richer air fueled their bodies. The combination made feats of flight possible that would now be out of reach. To tie it all together, think of a calm spiral above a swamp pool. The water is mirror still, broken only by the ripple of a rising amphibian or the splash of a falling leaf. Overhead, a griffin fly drifts lazily, adjusting its wings with the slightest tilt, letting the denser air do much of the work. It is not a frantic chase, not yet, but a demonstration of how an environment can shape possibility. The Carboniferous sky was not just a stage, it was a partner in flight. These mechanics reveal how atmosphere and anatomy intertwine. A creature's ability to fly depends as much on the air it moves through as on the wings it bears. In the Carboniferous, the denser, oxygen-rich sky gave insects the tools they needed to grow large and stay aloft. Lift was easier to find, glides were longer, and every wing beat counted for more. In that heavy air, giants soared, their size made possible by the very breath of their world. The Carboniferous swamp was more than just a backdrop of towering leucopsids and damp peat. It was a living web of connections. Every pool, every patch of moss, and every fallen log hid a tangle of lives linked together by who ate what and who avoided being eaten. These wetlands were not silent, though their sounds would have been different from modern forests. There were no birdsong or mammal calls yet, but the hum of insects, the splash of amphibians, and the soft rustle of creatures moving through fronds filled the night. Silent skies, except for the occasional crunchy snack. At the base of the food web lay the plants that built this world. Giant club mosses, tree-like horsetails, and seed ferns stretched across the swamps, their leaves, spores, and decaying litter feeding armies of detritivores. Millipedes, springtails, and early cockroach-like insects scurried across the forest floor, breaking down organic matter. The ground was alive with decomposers, creatures that turned dead wood and fallen leaves into the building blocks of new soil. Without them, the swamp would have been a suffocating mess of rot, but with them, nutrients cycled through the system, slowly but steadily. Among these detritivores were the giant millipede relatives like Arthropleura, which likely browsed on decaying vegetation. They were massive conveyor belts of digestion, turning heaps of dead plant matter into organic crumbs that enriched the ecosystem. Smaller detritivores darted in their wake, quick to capitalize on whatever they missed. Together they created a foundation that supported more complex layers of life. Above the decomposers came the herbivores. Insects with chewing mouthparts grazed on ferns and lycopsid leaves. Early relatives of grasshoppers, along with primitive beetles, explored stems and fronds. The plants themselves had few defences compared to modern flora. No bitter alkaloids, no thorny branches. So insects had a banquet of soft tissue available. Yet this ease of feeding made herbivores attractive targets for predators lurking just beyond the greenery. Predators came in many forms. Some were other insects, like carnivorous roaches and the early ancestors of ground beetles, scuttling hunters that made short work of smaller prey. Others were aerial giants such as Meganeura, sweeping the skies in search of unwary flyers. Their prey might include smaller dragonflies, mayflies, or even juvenile amphibians clambering too close to the water's edge. The swamps may not have had the roar of dinosaurs yet, but they were far from quiet, for the stillness of the night was punctuated by the sudden snap of jaws or the crunch of an exoskeleton. Amphibians were among the most conspicuous vertebrates in these coal forests. They came in a variety of sizes, from tiny salamander-like creatures barely longer than a finger to hulking labyrinthodonts that resembled crocodiles in miniature. These amphibians lurked in shallow pools, their eyes just above the surface, waiting for anything edible to drift within reach. Some specialized in insects, snapping them up as they skittered across the water. Others fed on fish, crustaceans, or smaller amphibians. It was a time when amphibians dominated roles later filled by reptiles, birds, and mammals. But reptiles were beginning to arrive. Early examples were small, lizard-like creatures that laid shelled eggs, a crucial innovation that freed them from relying entirely on water for reproduction. These early reptiles hunted insects on the forest floor, slipping silently among roots and fallen logs. Though modest in size, their appearance marked a turning point, the rise of a group that would one day give rise to dinosaurs and beyond. For now, however, they were simply another thread in the swamp's food web, eating insects while avoiding becoming meals themselves. Day and night painted different faces on this ecosystem. In the daylight, swarms of insects rose over pools, their wings glinting as they mated and laid eggs. Amphibians lounged in the warmth of the sun, conserving energy for sudden bursts of predation. Detritivores carried on their slow, steady business of breaking down the forest's endless supply of litter. By nightfall, the atmosphere shifted. The air cooled slightly, mist rolled over the wetlands, and predators took on a more active role. Giant griffin flies patrolled like shadows against the twilight, hunting in the dimming light. Small reptiles slinked across the damp ground, and amphibians became more daring, moving farther from the water's edge in search of prey. Even in the stillness of these wetlands, danger was everywhere. For an insect, survival meant constant vigilance. A misplaced wingbeat or a pause in the open could mean becoming dinner for something larger. Yet this constant pressure kept populations balanced. No single group overwhelmed the others, for each was checked by its predators and limited by its food supply. The result was a finely tuned community, where energy flowed upward from plants to herbivores, then to predators, and eventually back to the soil through decomposers. The diversity of invertebrates was staggering. Mayflies filled the air in great swarms, their brief adult lives dedicated to reproduction. Giant scorpions prowled the undergrowth, their armoured bodies gleaming in the swamp light. Spiders spun their first primitive webs, testing strategies that would later define entire lineages. Each of these creatures carved out a role, whether as predator, prey, or recycler. The sheer abundance of invertebrates ensured that energy pulsed through the food web in countless directions. One might picture the Carboniferous swamp as an orchestra without a conductor. Amphibians, insects, reptiles, and decomposers all played their part, their rhythms shaped by cycles of day and night, wet and dry. There was no central authority, no guiding hand, just the quiet logic of ecology unfolding over millions of years. In this intricate dance, a griffinfly's flight, a millipede's crawl, or a frog-like creature's leap were not isolated acts, but pieces of a grander whole. The food webs of these swamps reveal a world that was at once alien and familiar. Plants grew to unfamiliar heights, and insects reached sizes that seem impossible today. Yet the rules of life were the same. Eat and avoid being eaten, survive long enough to pass on your genes, and play your part in the circulation of energy. From the detritus at the forest floor to the gliding hunters of the skies, every creature was a link in chains that crisscrossed and overlapped, binding the swamp into a living, breathing community. It was a world without mammals, without birds, and without flowers, yet it thrived. The Carboniferous swamp was a place where silence was deceptive, where even in stillness the cycle of eating and being eaten went on without pause. And above it all, in skies heavy with oxygen, giants drifted and struck, a reminder that in this ancient world, the air itself set the stage for extraordinary lives. Fossils are not simply remnants of life. They are shadows captured in stone, fragments of moments that time refused to erase. In the case of giant insects and their Carboniferous neighbours, the evidence that allows us to reconstruct their stories comes in many forms. Some are delicate impressions pressed into fine-grained rock, others are darkened outlines etched in shale, and still others are the tracks and traces of movement across ancient mud. Each fossil is both a clue and a question, a reminder that what we know of these giants is always filtered through the patience of geology. Impression fossils are among the most striking. When an insect died and settled into soft sediment, its body could leave behind a detailed imprint before decomposition erased its form. These natural stamps sometimes preserve wings so intricately that even the delicate venation can be traced, offering insight into how ancient griffin flies once navigated the skies. The body itself might be long gone, but its outline remains, like a pressed flower forgotten in the pages of a book. Such impressions are fragile in origin but enduring in survival, giving us blueprints of creatures long vanished. In rare places called Lagerstätten, preservation reaches astonishing levels. These sites act like time capsules, freezing entire ecosystems in remarkable fidelity. Within them, paleontologists have uncovered not just hard shells or skeletal fragments, but also delicate structures such as wing membranes, soft tissues, and even the faint shimmer of pigmentation. For the Carboniferous, such deposits provide windows into a swamp world otherwise blurred by millions of years of decay. They remind us that the past was not vague or shadowy at the time, it was as vivid and immediate as today, and these fossils let us glimpse that reality again. Fire, too, has left its mark. The Carboniferous atmosphere was rich in oxygen, which meant that wildfires were frequent and often fierce. The presence of fossil charcoal known as fusane tells scientists not only that plants burned but also that oxygen levels were high enough to sustain widespread flames. These charred fragments are geological fingerprints of ancient combustion, preserved in coal seams and sediment layers. They help confirm atmospheric reconstructions, adding to the picture of an Earth that was lush, damp, but also periodically aflame. Not all evidence comes from bodies or plants. Coprolites, fossilized droppings, capture the less glamorous but deeply informative side of prehistoric life. A hardened pellet of ancient waste may contain fragments of insect cuticle, plant fibers, or even scales, revealing exactly what a creature ate. For giant millipedes, amphibians, or dragonfly-like predators, coprolites serve as direct evidence of diet. They are nature's unscripted notes, jotted down and buried, only to be read again hundreds of millions of years later. Trackways are another invaluable kind of fossil. When an Arthroplura crawled across damp sediment, its dozens of legs pressed patterned lines into the mud. Those tracks hardened into stone, enduring long after the body of the creature itself had vanished. From these rhythmic imprints, scientists can estimate the animal's size, gait, and even its speed. Trackways show behavior in motion, a record of activity rather than anatomy. They bring an eerie sense of presence, as though the creature had just walked past and might return at any moment. Understanding the age of these fossils requires careful dating of the layers in which they are found. Sedimentary rocks can be arranged like the pages of a book, with the oldest layers at the bottom and the youngest at the top. By correlating fossils across different regions and anchoring them with radiometric dating from volcanic ash layers, geologists establish timelines that stretch back hundreds of millions of years. Each fossil, then, is not just a physical object but a point on a calendar, helping to chart the unfolding story of life on Earth. Reconstructing ancient environments involves piecing together many lines of evidence. Plant fossils reveal the dominance of lycopsids and horsetails, while sedimentary structures hint at whether the setting was a stagnant swamp, a flowing river, or a coastal floodplain. Charcoal layers reveal the frequency of fires, while the types of invertebrates preserved show whether conditions were wet, dry, or fluctuating. By combining these details, paleontologists can breathe life into landscapes otherwise locked in stone. Yet fossils are rarely complete, and uncertainties abound. A wing impression in one location may not look identical to its counterpart in another. Was this a different species, or simply a variation of the same one? When two sets of tracks differ in width, are they the result of two distinct creatures or of one animal walking in softer versus firmer mud? Scientists must weigh these possibilities, comparing specimens across sites, examining microscopic details, and building cautious interpretations. The process is not unlike assembling a puzzle, with half the pieces missing and no image on the box to guide the way. Despite these challenges, fossils speak with quiet authority. They anchor imagination in reality, grounding reconstructions in evidence that can be studied, measured, and debated. They remind us that the Carboniferous world was not merely a fantasy conjured in retrospect, but a tangible, breathing reality that left its imprint behind. The outlines of wings, the scratches of legs in mud, the charred residue of a long-ago fire, all these whispers from stone testify to lives lived under ancient skies. There is a certain respectful wonder that comes from looking at such fossils. A faint outline on a slab of shale, no bigger than a hand, may be all that remains of a creature that once ruled the skies of its swampy world. To hold such a stone is to bridge hundreds of millions of years, to see in a shadow the spark of life that once darted, crawled, or fluttered. From these outlines, scientists weave living stories, restoring to memory what time had nearly erased. Fossils are not just relics, they are the translators of deep time. They take silence and turn it into narrative, absence and turn it into presence. Each impression, trackway, or coprolite is a reminder that the world we know today is built upon the layered echoes of worlds that came before. Through these shadows turned into evidence, the Carboniferous lives again, not as myth, but as memory etched into stone. It is tempting to imagine that the sheer abundance of oxygen alone explains the rise of giant insects in the Carboniferous swamps. After all, air thick with life-giving gas seems like the simplest explanation for wings that stretched wider than a hawk's, and millipedes the length of a car, but nature rarely acts with such simplicity. Oxygen was a major player, yes, yet it was not the only one pulling the strings. The drama of gigantism unfolded under the influence of many interconnected factors, ecological, climatic, developmental. And the true story is more nuanced than a single atmospheric dial being turned up. One idea focuses on the timing of predators. In the earliest Carboniferous forests, vertebrates that might have controlled insect sizes had not yet fully taken the stage. Amphibians were present, but they were relatively small and tied to water. Early reptiles were only beginning to explore terrestrial life. In other words, for a period, insects and their kin faced little threat from land-based vertebrate predators. Free from heavy predation, insect lineages could experiment with size, filling niches that might otherwise have been dangerous to occupy. Later, as reptiles diversified and became more effective hunters, the ceiling on insect size may have lowered, not because oxygen dropped alone, but because being enormous became riskier. In nature, being big is an advantage only if you can survive long enough to enjoy it. Competition also shaped possibilities. The Carboniferous forests were teeming with arthropod diversity, centipedes, scorpions, and the colossal Arthropleura among them. In ecosystems where niches are open and competition is moderate, organisms often expand into new roles. But once those roles become crowded, size can be checked by the presence of rivals. A giant insect could dominate in one window of time, only to be forced into decline when new competitors emerged. In this light, gigantism might not have been a permanent feature of insects, but a phase permitted by ecological opportunity. Temperature is another key part of the puzzle. The Carboniferous climate was warm and humid, but it was not uniform. Shifts in global temperatures affected metabolic rates, which in turn influenced how large an insect could grow while still functioning efficiently. Insects, being ectothermic, rely heavily on external conditions to regulate their activity. High oxygen levels may have opened the door to size increases, but only under certain thermal conditions would those increases have been sustainable. When temperatures shifted or extremes became common, the balance might have tilted against gigantism. Developmental biology adds another layer. Insects grow through a series of molts, and their size at each stage depends on how much time they spend in juvenile phases before reaching adulthood. A longer developmental timeline can allow for greater size, but it also increases vulnerability, more time exposed to predators, disease, or accidents before reproduction. If environmental conditions favoured extended juvenile periods, insects might have grown to giant proportions more easily. But if conditions changed to reward faster maturation, smaller sizes would prevail. Growth, in this sense, was not only a matter of oxygen availability, but also of life history strategies shaped by the risks and rewards of the Carboniferous world. The interplay of all these factors underscores the complexity of evolution. It was not that insects became large simply because oxygen allowed them to. Rather, oxygen created possibilities, while predation, competition, climate, and development determined how those possibilities were expressed. A griffinfly's wingspan or a millipede's length was not dictated by a single switch in the atmosphere, but by a chorus of influences acting together. Scientists studying this question today emphasize that evolutionary outcomes are rarely monocausal. Just as human height is influenced by genetics, diet, environment, and even social conditions, insect size in deep time was a product of multiple threads woven together. Elevated oxygen may have been the loom on which these threads were arranged, but the pattern itself was determined by many hands. In some ways, this layered explanation makes the story more fascinating. It shifts the focus from a single, oversimplified cause to a richer picture of ecological dynamics and evolutionary possibility. It invites us to imagine a world where insects grew not because they could, but because circumstances temporarily favoured it. And just as easily, those same circumstances could change, ushering in a different balance of size and survival. The rise and fall of giant insects, then, can be seen as a chapter in the constant negotiation between environment, biology, and chance. Oxygen was abundant, but so were opportunities and risks. Predators arrived, climates shifted, developmental strategies evolved. The result was a fleeting window in Earth's history when insects reached extraordinary dimensions. That they no longer do so today is not a mystery solved by a single variable, but a reminder that life's possibilities are always the outcome of many forces acting at once. In the end, the giants of the Carboniferous were not inevitable. They were the product of a unique convergence of conditions, a convergence that could just as easily have taken a different course. To understand them fully is to appreciate how intricate the web of causes behind any evolutionary event truly is. And that complexity, far from diminishing the wonder of their size, deepens it. For in every giant wingbeat or thunderous millipede's stride lies the story of life's astonishing ability to adapt when the world makes room. The age of giant insects did not end with a bang, but with a long and quiet retreat. Their disappearance was not a dramatic extinction, but a slow fade written into the changing air, shifting forests and evolving ecosystems of the late Paleozoic. Just as the giants rose because conditions briefly aligned in their favour, so too did they decline as the world gradually reshaped itself. One of the most important changes was the atmosphere itself. During the Carboniferous, oxygen levels were unusually high, reaching perhaps more than 1/3 of the air. This surplus was a gift to insects, whose tracheal breathing system became far more efficient under such conditions. But over millions of years, oxygen concentrations began to trend downward. By the late Carboniferous and into the Permian, levels were sliding closer to those we know today. The extra breathing room that had made enormous bodies possible was shrinking. A dragonfly with wings wider than a seagull's suddenly had less of the invisible support that once carried it through the air. The world's landscapes were changing too. The swampy lowlands that had dominated the Carboniferous began to dry. Great forests of lycopsids and other ancient plants gave way to seed ferns, conifers, and vegetation better suited to less waterlogged soils. As the coal swamps dwindled, so did the broad, damp habitats where oxygen production had been most intense. The new plants burned differently, altering fire regimes. In the Carboniferous, frequent fires had been fueled by oxygen-rich air and dense plant matter. As the balance shifted, fires changed in character, reshaping the ecosystems that insects had once dominated. The very stage that had allowed gigantism was being dismantled piece by piece. A gradual drying of climate added another layer of pressure. The late Paleozoic was marked by periods of aridity, punctuated by swings in temperature and rainfall. Wetlands that once stretched endlessly were increasingly broken into patches, less reliable and more fragmented. Giant insects that thrived in vast humid expanses faced a patchwork world where resources were more scattered. Smaller, more adaptable species had an advantage under these less predictable conditions. Evolution tends to reward flexibility, and giants are often less flexible than their modest cousins. Predation also began to catch up. In the Carboniferous, insects had relatively little to fear from vertebrate hunters, but as time moved forward, amphibians and reptiles diversified, some becoming more efficient insect eaters. Later, much further into evolutionary time, birds and bats would take to the skies, forever changing aerial competition. The towering griffin flies of the Carboniferous never faced a falcon, but over the long arc of time, vertebrate predators narrowed the window for gigantism. Being large and conspicuous in a world with agile, hungry hunters eventually tipped from being an advantage to being a liability. The decline of giant insects was not the work of any single force. It was the outcome of many overlapping trends: air growing thinner of oxygen, climates growing harsher, forests transforming, predators arriving. Each of these pressures chipped away at the giant's success. It was not sudden collapse, but a long unweaving, spread across millions of years. If one could step into the late Paleozoic, the skies might still hold impressive insects, but they would not be quite as outsized as their ancestors. The ground might still show the traces of large arthropods, yet their reign was waning. The story is a reminder of how delicate evolutionary opportunities can be. Gigantism was not an inherent destiny for insects, but a possibility created by specific conditions. When those conditions changed, the possibility faded. It did not vanish overnight, but like the dimming of twilight, it receded until only memory and fossils remained. The long fade of the giants illustrates the quiet power of gradual change. Oxygen levels drifted downward by just a few percentage points, but that small difference transformed what bodies could sustain. Forests shifted from spongy swamps to drier, fire-prone woodlands, and with that shift, whole ecosystems reorganized. Predators that began as minor players grew into major forces. Each factor alone might not have ended gigantism, but together they wrote a slow epilogue to the age of the Titans. Insects did not vanish, of course. They endured, diversified, and remain today the most numerous and adaptable animals on Earth. Their smaller size became not a limitation, but a key to survival, allowing them to slip into every imaginable niche. The legacy of the Carboniferous giants is not just their fossils, but the lesson that evolution constantly balances possibility with constraint. When the air thickened with oxygen, wings could stretch wider and bodies could grow longer. When the air thinned and the world changed, the balance shifted back. The decline of giant insects was, in the end, not a fall but a return to sizes better matched to the planet's new atmosphere, new plants, and new predators. Their reign was extraordinary but temporary, and that transience is part of what makes it remarkable. They remind us that even the most impressive adaptations are always provisional, always tied to the conditions of their time. And when those conditions change, as they inevitably do, life reshapes itself once again. In a world where dragonfly-like insects stretched as wide as modern gulls and millipede cousins sprawled longer than a car, it is tempting to imagine that everything alive in the Carboniferous was oversized. Yet most creatures remained modest, navigating the same swampy forests and heavy air without ever taking on titanic proportions. The truth is that scaling in nature is a set of trade-offs, not a ladder of progress. Bigger is impressive, but small can be just as successful, sometimes even more so. There was plenty of room at the tiny table, and it was often full. Small size brought with it a remarkable set of advantages. A small insect needs less food to survive, which is a great insurance policy in an unpredictable environment. If drought or fire struck, or if a patch of forest collapsed into a bog, a tiny creature could endure on crumbs where a giant might starve. Small bodies also allowed rapid reproduction. Many small insects could go from egg to adult in a single season, turning over generations quickly. That meant faster adaptation, quicker recovery from setbacks, and an almost endless capacity to experiment with new forms and behaviours. In evolutionary terms, short life cycles can be a superpower. When conditions change, species that reproduce rapidly can test out many genetic variations in a short span of time. Some of those variations fail, but others stick, giving small-bodied insects the flexibility to ride out climate swings or ecological shifts. The giants of the Carboniferous were locked into slower rhythms. Their size demanded more energy, more time, and more risk. Small species, by contrast, could dart between niches, producing offspring that tried different survival strategies almost as fast as the environment itself shifted. The ecological mosaic of the Carboniferous was not simply a stage dominated by a handful of giants. It was instead a layered tapestry, where small beetles, roaches, and early relatives of modern insects crept in leaf litter, pollinated primitive plants, and recycled nutrients. While the griffin flies hunted in the open skies, these smaller forms worked quietly in the undergrowth, shaping ecosystems in less conspicuous but equally important ways. The presence of giants did not erase the value of the modest. In fact, the very survival of large species often depended on the teeming abundance of smaller prey, pollinators, and decomposers. Scaling rules are at the heart of why smallness remains so successful. When a body doubles in size, its volume, and therefore its weight, grows much faster than its surface area. That creates challenges for oxygen delivery, mobility, and structural support. A giant insect's tracheal tubes must reach deeper, its exoskeleton must be sturdier, and its energy demands higher. By contrast, a small insect operates in a zone where diffusion works efficiently, muscles face less strain, and surfaces easily support weight. Physics itself carved out an enduring advantage for small creatures, one that sheer size could never override. Mobility was another quiet benefit. A small insect can squeeze into spaces between roots, slip under bark, or hide beneath leaves. Large species, no matter how powerful, cannot easily exploit such microhabitats. These hidden corners of the Carboniferous world offered safety, food, and breeding grounds that giants simply could not reach. In that sense, the giants ruled the skies and opened paths, but the smaller forms ruled almost everywhere else. Even resilience to environmental upheaval tilted toward the small. When oxygen levels began to fall from their Carboniferous highs, large-bodied insects found it harder to maintain the same performance. Small-bodied species with lower demands and simpler breathing pathways barely noticed the shift. Their survival was not tied to a narrow atmospheric sweet spot, making them more enduring as climates dried and forests changed. Giants may capture the imagination, but the modest endured through every rise and fall of the Paleozoic. It is worth remembering that in ecology, better is never absolute. Large size brings dominance in hunting or intimidation, but small size brings stealth, adaptability, and persistence. Neither is superior in all circumstances. Each is simply a different solution to the puzzle of survival. In the Carboniferous, those solutions coexisted. The skies could host a predator with wings like a kite, while the soil just below wriggled with creatures no larger than a grain of rice. Both belonged to the same world, both thrived in their own way. A touch of humour helps to frame this balance. Imagine a banquet laid out in a swampy forest clearing. The giants may stride in, towering and dramatic, but they would quickly find the buffet crowded with 1,000 tiny diners already nibbling away. There was indeed plenty of room at the tiny table, and in many respects it was the busiest, noisiest, and most enduring place to be. The legacy of the Carboniferous is not only the spectacular size of its giants, but the persistence of its smallest inhabitants. The beetles and cockroaches that scuttled unnoticed through the undergrowth had the last laugh, surviving into the modern world while their oversized cousins faded into stone impressions. The lesson is simple yet profound. Evolution does not always reward grandeur. More often, it rewards balance, efficiency, and resilience. Smallness, in its quiet way, is one of evolution's greatest triumphs. While giant insects painted the skies with awe, it was the smaller ones that ensured continuity, shaping ecosystems from beneath the shadows of towering lecopsids and lumbering arthropods. Their legacy is written not in spectacular fossils alone, but in the living insects of today, which still dominate nearly every environment on Earth. The giants may be gone, but the small have never ceased to thrive. Stories of ancient giant insects tend to spread like wildfire, sometimes leaving facts singed and distorted in the process. The Carboniferous world certainly produced creatures that would be startling if encountered today, but the details are often stretched in retellings until they resemble something closer to a creature from a monster film than from the fossil record. It helps to sift calmly through what the evidence actually shows, separating the swamp stories from the science. Take Meganeura, often introduced as a dragonfly the size of a hawk. It was in truth not a dragonfly at all, but a member of an extinct order called the griffin flies. These insects looked similar to dragonflies, with long bodies and paired wings, but they were an evolutionary side branch, not direct ancestors of modern Odonata. Their wingspans reached around 70 centimetres, roughly the width of a human arm, or about the size of a large dinner tray. That is large enough to be impressive without needing to imagine them blotting out the sun like pterosaurs. A griffin fly would have been an aerial hunter, but it was still just an insect, not a mythological beast. Cockroaches also fall victim to exaggeration. Headlines sometimes suggest that roaches once grew to the size of small dogs. The fossil record tells a more measured tale. Carboniferous cockroach relatives, sometimes called roachoids, did grow larger than most of today's kitchen dwellers, with some reaching several inches in length. Picture a cockroach about the size of a modern smartphone, not a beagle. Unsettling perhaps, but not quite the horror imagined by sensational accounts. Their abundance had more to do with the lush, damp forests that offered ample detritus to feed on than with any monstrous size. Centipedes, or rather their distant relatives, also inspire lurid descriptions. Arthropleura, the great millipede-like arthropod, is often described in tones more fitting for a sea serpent. It truly was immense for a land invertebrate, with estimates suggesting lengths of up to 2.5 meters. Yet even here the record needs nuance. Trackways and partial fossils point to impressive size, but full specimens are rare, and most individuals were probably smaller. Arthropleura would not have been slithering through every swamp like a recurring nightmare. Instead, it occupied particular habitats, feeding primarily on plant material and detritus. Enormous compared to modern millipedes, yes, but not an unstoppable terror. It is also worth addressing the way oxygen levels are framed in popular accounts. Sometimes the Carboniferous atmosphere is described as if it contained twice as much oxygen as today, instantly inflating every insect to comic book proportions. Oxygen was indeed higher, with estimates ranging from 30 to 35% compared to today's 21%. But the effect was not uniform across all species. Large size became possible for some insects because their respiratory systems worked more efficiently in that oxygen-rich air. but many insects remained small. The giants were exceptions, not the universal rule. Sensational headlines sometimes give the impression that these giant insects were constant hazards, swooping on unsuspecting amphibians or battling like monsters from a prehistoric arena. The reality was more prosaic. Insects, even large ones, still operated within the constraints of their biology. They needed to find food, avoid predation, and navigate their environments just as smaller species did. A griffin fly was an efficient aerial predator, but it was not clearing the skies of everything that moved. An Arthropleura was a giant detritivore, not a rampaging carnivore. Myths add drama, but the truth is that these creatures were fascinating without needing embellishment. For a sense of scale that sticks, it helps to think in familiar terms. Imagine holding a modern ruler. The largest dragonflies today measure a bit over half of it in wingspan, while Meganeura could cover its full length and more. A smartphone-sized cockroach fossil might not appeal to those with an aversion to scuttling insects, but it is a manageable mental image, more unsettling curiosity than nightmare. As for Arthropleura, picture a coffee table that occasionally wriggled. These benchmarks are memorable without drifting into exaggeration. Another myth worth clearing is the idea that giant insects disappeared overnight with the drop in oxygen. Decline was gradual, and smaller insects were present throughout. As conditions changed, it was simply the smaller forms that endured more easily. The Carboniferous giants had their time in the spotlight, but they didn't vanish in an instant. Fossils show a slow fading, not a sudden catastrophe. All of this points to a broader truth about paleontology. Fossil evidence is remarkable, but it also requires careful interpretation. A single wing impression can give clues about wingspan, but reconstructing the life of the animal requires comparisons with other fossils and with modern analogues. When scientists speak of griffin flies, cockroaches, or Arthropleura, their claims rest on detailed examination, not on legend. Myths, by contrast, grow in the gaps of uncertainty, filling them with drama that nature does not always provide. Debunking these myths does not strip away wonder. In fact, it enhances it. Knowing that griffin flies were not dragonflies, but a distinct evolutionary path, makes them more interesting, not less. Understanding that giant cockroaches were only smartphone-sized allows us to appreciate just how adaptable these insects have been, persisting in various forms for hundreds of millions of years. Recognizing that Arthropleura was a peaceful detritivore highlights the diversity of ecological strategies long before mammals or birds existed. The Carboniferous world was already extraordinary. Towering forests built the coal seams still burn today, oxygen filled the air at levels unmatched in later ages, and ecosystems flourished with strange and beautiful life. The truth, steady and grounded, is more rewarding than any swamp story. Facts, when seen clearly, carry their own quiet magic, no embellishment required. The idea of giant insects returning has a certain allure, equal parts fascination and quiet dread. After all, the Carboniferous swamps once supported griffin flies with wingspans wider than a person's arm and millipede-like arthropods stretching several meters long. If it happened before, could it happen again? The answer requires a careful look at both the ancient conditions that allowed those giants to thrive and the realities of today's world. The first and most obvious factor is oxygen. During the late Carboniferous, atmospheric oxygen peaked at roughly 30 to 35%, compared with the 21% of today. That boost made insect-breathing systems more effective. Insects do not have lungs. They rely on a branching network of tiny tubes called tracheae, which deliver oxygen directly to tissues. The higher the oxygen concentration in the air, the farther it can diffuse down those tubes, supporting larger bodies without starving tissues of breath. For an insect dreaming of grandeur, the atmosphere was doing much of the heavy lifting. But oxygen alone was not the whole story. The ecosystems of the Carboniferous were different in ways that helped giants find their place. dense, swampy forests offered abundant vegetation and detritus, while amphibians and early reptiles were not yet efficient aerial hunters. In that ecological window, a griffin fly could dominate the skies with little competition, and a massive arthroplura could roam the forest floor with few predators capable of tackling it. The giants existed not in isolation, but within a very particular set of environmental circumstances. Could those conditions return naturally? Atmospheric oxygen fluctuates with global processes driven by the balance of photosynthesis and respiration, burial of organic carbon, and geological cycles. While oxygen may rise modestly again in Earth's distant future, it is unlikely to approach Carboniferous highs. Today's ecosystems also include a cast of predators, birds, bats, and small mammals that are perfectly suited to keeping insect size in check. Even if oxygen climbed, the selective pressures of predation would act as a ceiling, discouraging insects from growing too large. An oversized insect would be a slow-moving buffet for any sharp-eyed bird. Another limiting factor is the exoskeleton itself. For an insect, growth means periodic molting. The outer cuticle must be shed, leaving the body soft and vulnerable until the new one hardens. For a creature the size of a dinner plate, this is already risky. For something even larger, the dangers compound. The weight of the body could crush its soft frame before the cuticle sets, or predators could seize the opportunity. Giant arthropods of the Carboniferous managed the process, but the physics of scaling impose strict limits. The bigger the body, the greater the engineering challenge of safely molting. Tracheal delivery also scales poorly. Oxygen diffusion is efficient over small distances, but struggles across larger bodies. Even in oxygen-rich air, this system is not easily upgraded. Vertebrates solved the problem with lungs and circulatory systems, pumping oxygen actively around the body. Insects remain bound to a passive method. Evolution tinkers, but the tracheal system is not easily re-engineered into something that could sustain a truly massive creature in modern conditions. Speculative scenarios often imagine genetic engineering as a shortcut. Could humans, with the tools of biotechnology, design an oversized insect and raise it in controlled conditions? In theory, some enlargement might be possible, but in practice, the hurdles are immense. Beyond respiratory limitations and molting risks, such a creature would struggle in the presence of today's predators. Even in a protected lab, the ethics of engineering animals for spectacle would raise pressing concerns. Creating a giant dragonfly might make for dramatic headlines, but the welfare of the creature and the ecological consequences would be serious questions to answer. And then there is the matter of ecosystems. Modern environments are finely balanced. Introducing oversized insects would not just add new curiosities, it could ripple through food webs in unpredictable ways. Invasive species already demonstrate how small shifts can disrupt ecological stability. A giant insect, even if it could survive, would not fit neatly into existing niches. Responsible science asks not just whether something is possible, but whether it should be pursued. All of this circles back to a quiet conclusion. The Carboniferous giants were products of their time, emerging from a unique combination of high oxygen, swampy habitats, and limited predators. Today, the stage has changed. Oxygen levels are lower, vertebrate predators dominate the skies, and the biological constraints of insect anatomy remain. Even with human intervention, the barriers are daunting and the ethical concerns even greater. Could giant insects return? Probably not. The physics of breathing, the vulnerabilities of molting, the gauntlet of birds and bats, and the intricacies of ecosystems all stack the odds firmly against them. Their age has passed, preserved in stone impressions and carbonized fragments rather than in living forests. But there is comfort in this too. The fossil record allows us to know they once lived, and imagination allows us to picture their world. The giants need not return to inspire awe. They have already left their legacy in stone, and in the quiet wonder they still stir today. The light fades slowly across the ancient swamp. Shadows lengthen beneath the tall trunks of lycopsid trees, their scaled bark catching the last hints of evening glow. The air grows cooler but remains heavy with moisture, every breath touched by the earthy perfume of damp peat and living plants. A hush settles, though it is not silence. The swamp never truly sleeps. It simply changes its voice when the sun dips. The ground is soft underfoot, carpeted with fallen leaves of giant ferns and layers of moss that drink in the day's humidity. Each step releases the faint scent of decay, sweet and almost smoky, a reminder that this forest is also a factory, turning sunlight into biomass, and biomass into peat that will one day, in deep time, become coal. The thought is a quiet, factual aside, barely intruding into the stillness. These damp cycles are building something immense for a world yet unborn. Dew clings to fronds and glistens like glass beads, gathering in the folds of horsetail stems and the feathered spread of seed ferns. Water drips steadily from higher branches, a soft, irregular rhythm that punctuates the night. Somewhere in the darkness a small amphibian stirs, the faint plop of its movement vanishing into the swamp pools. Early reptiles, still few in number, tuck themselves into safe crevices, preferring the protection of stillness as the swamp's nocturnal voices rise. A faint tremor passes in the air, a low thrum that might be mistaken for the pulse of the earth itself. But then it comes again, steady and deliberate, the wing beat of a large griffin fly gliding through the dusky canopy. Its silhouette passes briefly across the dim sky, wings catching what little light remains, shimmering for a heartbeat before vanishing. The flight is unhurried, a calm spiral over the mirrored surface of a still pool, hunting perhaps, or simply patrolling. The swamp carries its own kind of silence, made not of absence but of softness. Crickets and smaller insects chirr in the background, a constant pulse. Water shifts and settles. The occasional rustle in the ferns marks the passage of something unseen, perhaps a small arthropod scuttling among fallen branches. Every sound is cushioned, wrapped in the dense air, never sharp, never hurried. The towering trees rise into the darkness, their trunks impossibly straight, their crowns spreading in fronded silhouettes. Some stand like ancient columns, others arch where lightning or decay has carved openings in the canopy. The scale of them is humbling. Lepidodendron, with trunks as thick as a person is tall, stretching 30 meters into the sky. Beneath them, the horsetails rise like clustered spears, while seed ferns unfurl broad leaves that capture moonlight in pale glimmers. The forest is an architecture of living stone, a cathedral of green. A trackway lies across the peat, faint but visible in the sheen of dew. Wide, parallel impressions, each the size of a dinner plate, wander into the darkness. It is the footprint of an Arthropleura, the great millipede-like giant, though the creature itself is not in sight. Perhaps it passed earlier in the day, searching for decaying matter among the forest floor, or perhaps it lingers nearby, still and careful, as if even its vast form is mindful not to disturb the tranquillity of the night. A breeze rises for a moment, subtle and cool. It carries with it the mingled scents of the swamp, sharp resin from crushed plant stems, earthy peat from the ground, the sweetness of fern spores waiting for the morning air to lift them into dispersal. It is a reminder of how the forest breathes not only oxygen, but also the chemistry of reproduction, sending invisible clouds of spores drifting like unseen snow. Overhead the stars are faint, blurred by the canopy and the thickness of the air. The denser atmosphere of this age bends light differently, softening the outlines of the heavens. What shines through is filtered, muted, almost dreamlike. The sky is less a window and more a dome, pressing close, intimate, yet unreachable. The quiet of the swamp invites reflection. Here, the giants of the Carboniferous move at their own pace, with no sense of urgency. Growth and decay, flight and stillness, light and shadow. They all flow together in cycles measured not in days but in geological time. A griffin fly's wing beat is a fleeting moment. A peat bed forming beneath your feet is a story written over millions of years. Both coexist in this one night, in this one stretch of breath. A final sound drifts through the air almost like a sigh. It is the creak of a lycopsid's trunk shifting, a slow bow under the weight of its crown. The forest adjusts itself gently, as though stretching in its sleep. Nothing is in a hurry here. The swamp does not rush. It simply endures, layer upon layer, building futures far beyond the creatures that walk among its roots. And in this moment of stillness, in the thick air of a cold forest night, the world feels vast yet hushed. Each drop of dew, each thrum of a wing, each drifting spore carries the quiet weight of deep time. The night does not ask for attention. It simply is, and in that simple being it becomes something almost eternal. When scientists look back at the giants of the Carboniferous swamps, they're not simply gawking at oversized curiosities. They're examining prototypes, natural experiments in how far biological design can be pushed under particular conditions. These ancient insects and arthropods are lessons wrapped in exoskeletons, wings and trackways, and they still shape the questions researchers ask today. One of the first lessons comes from scaling laws. When an animal doubles in size, its volume and weight increase much faster than its surface area. This means that the systems handling gas exchange, strength, and movement face exponentially greater demands. A modern insect cannot simply scale up to the size of a dinner plate because its respiratory tubes and exoskeleton would not keep pace with its mass. In the Carboniferous, higher oxygen levels buffered this imbalance, but only to a point. The biology of those creatures reminds scientists that every structural design, whether natural or engineered, comes with hard mathematical limits. Respiration is perhaps the clearest example. Insects breathe through tracheal tubes that allow oxygen to diffuse directly into tissues. In a world with oxygen levels higher than today's, diffusion could sustain much larger bodies. Modern engineers studying diffusion and surface-to-volume ratios use these ancient case studies to think about how biological systems might operate under altered atmospheres. It is a reminder that biology does not invent miracles. It operates within the chemistry and physics of its surroundings. These scaling principles do not just matter to paleontologists. Engineers working on robotics and drones often find inspiration in insect wings. Though Meganeura and its kin are long extinct, their fossilized wings show branching veins and supportive cross structures that distributed stress efficiently during flight. When researchers build lightweight flying machines, they sometimes mimic these vein networks, creating rigid but flexible wings that handle turbulence more smoothly. The idea is not to literally copy a Carboniferous giant, but to recognize that nature's trial and error has been running for hundreds of millions of years. Compared to that, human research and development is only just leaving the nest. Nature's R&D has very long timelines indeed. Of course, modern drones operate in very different conditions than prehistoric insects. Our atmosphere is thinner in oxygen, and the materials engineers use are metals, polymers and composites, rather than chitin. Still, the fundamental principle of distributing stress across a wing surface or reducing weight while maintaining strength remains the same. Fossil wing impressions are not blueprints, but they provide inspiration, proof that solutions exist to the problems of lightweight flight, even if the context is separated by vast ages. The study of ancient air has relevance far beyond flight mechanics. Oxygen levels are intimately tied to climate, vegetation, and fire. In the Carboniferous, oxygen concentrations may have reached levels of 30% or higher, far above the 21% of today. This oxygen-rich world meant not only giant insects but also a heightened risk of wildfires. Plant matter, once dried, could ignite and burn more easily, and charcoal deposits from this era serve as geological markers of ancient fire regimes. For modern climate scientists, these records are invaluable. They show how changes in atmosphere and vegetation interact to influence fire frequency, a lesson with pressing importance today as forests around the globe experience shifts in fire patterns under human-driven climate change. Coal deposits themselves hold lessons too. The accumulation of vast peat swamps, compressed into coal seams, locked away gigatons of carbon. This deep burial of plant matter dramatically altered Earth's atmosphere, helping to regulate greenhouse gases over millions of years. Understanding how these ancient processes worked informs not only paleoclimatology, but also modern carbon cycle research. The long fade of the Carboniferous giants parallels shifts in oxygen and climate that resonate with present-day questions. How does atmospheric composition shape ecosystems, and how do ecosystems in turn reshape the air? Scaling rules also help explain why certain designs endure. Small insects continue to thrive today, not because they fail to grow large, but because being small is often the better trade-off. Rapid reproduction, resilience to predation, and ability to exploit tiny ecological niches give them an edge. From an engineering perspective, this is a reminder that bigger is not automatically better. Sometimes efficiency, adaptability, and subtlety are the true measures of success. An ant colony may weigh less than a sparrow, yet its collective impact on soil and ecosystems rivals that of much larger creatures. There is also a cultural angle to these scientific lessons. Stories of giant dragonflies and millipedes capture public imagination, but when framed accurately, they can also help communicate broader truths. Teachers and science communicators use these spectacular examples to highlight how ecosystems, atmosphere, and physics interconnect. By tracing the rise and fall of these arthropod giants, people see that life is not static but deeply shaped by its environment. It is a humbling reminder that organisms and atmosphere co-create one another in a feedback loop stretching across eons. The broader implication is one of perspective. By studying these long-vanished creatures, scientists gain not only specific insights into scaling, respiration, and flight, but also a clearer sense of the boundaries within which all life must work. Biology does not cheat physics. It negotiates with it. The massive griffin flies and lumbering Arthropleura were not violations of natural law, but expressions of what was briefly possible under conditions unlike today's. That recognition helps modern science frame new questions in fields as diverse as robotics, ecology, and climate modelling. In the end, the lesson is one of balance. The giants remind us of possibilities unlocked by shifting atmospheres, but also of limits imposed by structure and scale. Their legacy lies not just in fossils pressed into shale, but in the way they continue to guide scientific imagination. From drone wings patterned after ancient Venation to fire models calibrated with Carboniferous charcoal, the echoes of those swamp dwellers ripple through modern thought. Nature, after all, has been running experiments for hundreds of millions of years. Humans are only just beginning to catch up. Beneath many landscapes of today, far below forests, cities, and farmland, lie the remnants of ancient swamps. What now fuels power plants, heats homes, and drives industry once stood as towering lycopsids, horsetails, and ferns beneath a humid Carboniferous sky. Coal is not simply a black rock, it is a time capsule of carbon, compressed sunlight, and ancient breath, sealed away for hundreds of millions of years. Its story links the rise of giant insects, the fall of ancient forests, and even the industrial revolutions of humanity. During the Carboniferous, dense swamp ecosystems thrived across vast lowlands. Plants grew tall and fast, locking away carbon through photosynthesis. Much of their woody tissue contained compounds like lignin that microbes of the time struggled to break down. When these trees and ferns toppled, their remains often accumulated in stagnant, waterlogged soils where oxygen was scarce. Instead of decaying fully, they built thick mats of peat. Over millions of years, layers of sediment buried these peat beds, compressing them under immense pressure and heat. The transformation was gradual. Peat hardened into lignite, then bituminous coal, and in some cases into the hard, shiny anthracite. Each seam represents countless generations of vegetation compacted into a geological library. This burial of carbon had planetary consequences. By locking away so much plant matter underground, atmospheric carbon dioxide levels fell. Oxygen, produced but not reabsorbed by decay, accumulated to levels significantly higher than today. The very conditions that allowed giant arthropods to thrive were tied to this burial. The coal swamps were not only habitats, they were planetary engineers, altering the chemistry of the air and tipping feedback loops that reshaped climate. Fast forward hundreds of millions of years, and humans discovered these seams of fossil sunlight. Coal fueled the engines of the 18th and 19th centuries, driving industrial revolutions and global transformation. The energy stored in those ancient forests launched trains across continents, powered steel furnaces, and electrified cities. In doing so, humanity re-released carbon that had been locked away since dragonflies the size of hawks and millipedes. The length of cars roamed the earth. It is one of the most striking examples of deep time reaching forward to shape human destiny. Yet this story carries a second lesson. What took millions of years to store can be returned to the sky in mere centuries. Burning coal rapidly increases atmospheric carbon dioxide, altering climate in ways eerily reminiscent of ancient shifts. The balance between atmosphere and life that once enabled giants can be pushed in the other direction as well. By examining the Carboniferous record, scientists see how feedbacks between plants, air and climate operate over long timescales. These insights warn of both resilience and vulnerability. The coal record also helps scientists reconstruct ancient environments. Within seams, paleobotanists find impressions of leaves, bark and spores, while geologists analyse isotopes to deduce past temperatures and oxygen levels. Even charcoal fragments preserved in coal tell stories of prehistoric wildfires. Together, these time capsules reveal how vegetation, climate and atmosphere dance together through feedback loops. When plant growth surged, carbon burial increased, tipping the system toward cooling. When swamps dried, carbon release and fire returned, shifting the balance again. Life and air co-evolved, each altering the other in a dynamic exchange. This interdependence has a calming but profound implication. The Earth is not a passive stage on which life acts. It is a co-creator. The Carboniferous swamps built the air, just as the air shaped the swamps. Feedbacks like these run quietly across eons, steady yet immense. Insects, amphibians, trees and microbes all contributed to this shared experiment. By studying their outcomes, modern science gains a sense of both humility and perspective. There is also something quietly poetic in knowing that every flicker of a coal flame once came from sunlight that filtered through fern fronds more than 300 million years ago. The warmth in a hearth, or the power driving a machine connects, in a chain of transformation, back to a humid swamp buzzing with giant wings and rustling leaves. Even as society transitions away from coal, its legacy remains a reminder of how deeply human history is entangled with geological history. The Carboniferous teaches that planetary systems have limits, but also rhythms. Oxygen soared, then declined. Giants rose, then faded. Forests expanded, then collapsed under changing climates. The coal seams left behind are not merely fuels, they are records of these cycles written in compressed carbon. Reading them allows us to glimpse the grand scale at which life and Earth together shape possibility. And in this reflection, there is a kind of gentle landing. The great insects are gone, their forests buried, their atmosphere altered. Yet their legacy persists in the energy that once ran steam engines, in the scientific models that trace climate feedbacks, and in the quiet reminder that life is never separate from its world. The Carboniferous swamps, through their transformation into coal, continue to speak across time. They remind us that everything in nature is connected: air, water, soil, and life, woven into feedbacks that hum along for millions of years and occasionally whisper into our present. Across this journey through deep time, one theme has emerged again and again. The size of life is never a matter of chance alone. It is always negotiated, shaped by the invisible mathematics of air, the limits of physics, and the shifting landscapes of ecology. The griffin flies that hovered above Carboniferous swamps did not grow to hawk-sized proportions simply because they wanted to. They expanded into a world where oxygen was abundant, predators were scarce, and the air itself allowed wings to bear their weight. The vast millipede-like Arthropleura was not a monster conjured from imagination, but an animal tuned to the resources of its forest floor, following the rules of growth that all creatures must obey. The laws that guided them are the same laws that guide dragonflies today, or the sparrows outside a window. Physics does not bend, even for giants. Every living thing is a balance between opportunity and constraint, advantage and trade-off. The insects of the coal swamps reached their extraordinary dimensions not because life had broken free of limits, but because for a fleeting window of time the boundaries shifted. To see this clearly is to appreciate both the wonder and the humility of biology. Nature does not deal in absolutes, it works in negotiations. Oxygen rises, and lungs or tracheae stretch to fill the surplus. Predators appear, and wings refine their turns, their speeds, their stealth. The exoskeleton, a marvel of armour and flexibility, becomes both shield and burden. Every adaptation solves a problem while creating another. The giants remind us that every advantage carries a cost, and every design comes with its own fragility. The meditative walk through the coal swamp, ferns brushing with dew, air thick with damp earth, and the hush of night alive with faint wing beats, offers more than atmosphere. It embodies the lesson. Life is never alone. It is always in dialogue with its environment. Each scent, each shadow, each drop of condensation is part of a larger system that shapes and sustains. The swamp itself was an organism, a breathing tapestry of mosses, trees, insects, amphibians, and sky. From such connections came the vast deposits of carbon that would one day power human history. From such connections came both the rise of giants and their eventual decline. Even in their fading there is calmness. The disappearance of giant insects was not a sudden catastrophe, but a gradual shift as oxygen declined, as forests changed, as vertebrate predators eventually took to the air. The story is not one of tragedy, but of transitions. Life flowed into new shapes, new scales, new possibilities. Small creatures found their own advantages, proving that bigger was not always better, only different. The tiny too had their table set in the great feast of evolution. There is a quiet beauty in recognizing that nothing in nature stands apart. The coal seams beneath our feet, the air we breathe, the forests that spread across continents, all are joined by the same threads of carbon and oxygen, captured, released, and captured again. To look at a fossil wing etched in stone is not only to see an insect, but to see atmosphere, fire, forest, and time compressed into a single outline. And so the story settles into stillness. Picture again the wide expanse of a Carboniferous swamp. The water is calm, mirroring the towering trunks that rise into a dim green haze. A great insect, its wings as long as an arm, glides in slow spirals above the surface. It does not hurry. The air is heavy enough to carry it, the forest quiet enough to give it space. Below, amphibians stir in the shallows, and fronds nod gently with the weight of dew. The night is hushed yet alive with breath. In that scene lies the essence of the tale, life adjusting, balancing, negotiating with the elements around it. The physics of wings, the chemistry of air, the ecology of swamps, all converge into the simple grace of flight across still water. It is serene, timeless, and humbling. And in that serenity, curiosity can rest easy. The giants have gone, but the questions they leave behind continue to guide us, about limits, about possibilities, about how deeply life and planet entwine. The ancient wings may be folded in stone, yet their echoes remain in every breeze, every rustle, every fragile thread of connection between Earth and the creatures it sustains. The night closes gently over the swamp and the image lingers, wings gliding in silence, water holding their reflection, the air heavy with mystery. The story of giant insects ends not with noise but with calm, an invitation to wonder, and then to quiet. If you enjoyed this quiet flight through deep time, a simple way to help is by leaving a like. It tells the algorithm that this kind of content is worth sharing, and it helps more curious minds find their way here. Subscribing keeps you close for the next journey, and turning on notifications ensures you never miss when a new story unfolds. If there is a topic you would love to see explored, whether another chapter of ancient life, a strange corner of science, or a mystery of the cosmos, share it in the comments. Every recommendation helps guide what comes next. Until then, thank you for listening, and may your curiosity carry you gently forward.